Notice that the mean, 69 inches, is right in the middle. So if I said, what percent of adult men in the United States are less than 69 inches tall? If I draw a line right at the 69-inch point, right in the middle, and take everything that's to the left of that, on the low side of 69 inches, that turns out to be 50% of the total area. Exactly half of this is over here to the left of 69 inches. So 50% of men are below 69 inches, and the other 50% are above 69 inches in height. What percent of men are between 66 and 72 inches tall? What does it look like to you if you had to guess what percentage of this is shaded? Well, it turns out to be about 68%. So about 68% of men fall within that interval between 66 and 72 inches tall. And then that leaves 16% who are below 66 inches and 16% who are above 72 inches. What percent of men are between 63 and 75 inches tall? About 95% of them. So that leaves only the other 5% of men who are outside that range. 2.5% of men are less than 63 inches tall. That would be less than 5'3". And 2.5% of men are more than 75 inches tall, which would be 6'3". What percent of men are less than 65.4 inches tall? So if I just find that point on my scale, draw a line there, and less than that would be everything on this side of that point. And when I ask what percent of men are less than 65.4 inches tall, I'm asking about, okay, what percent of this region is over here? You want to take a guess? I don't expect you to guess it exactly, but I hope your guess was at least a lot less than 50%, because that definitely, I can see that's less than 50% of the whole thing. So it turns out that it's about 11.5%. So 11.5% of men are below 65.4 inches in height, and that leaves the other 88.5% who are above that height. And one of the things we'll see in this chapter is how to answer questions like this, how to come up with numbers like, oh, this is 11.5%. Now, in the example we've been talking about here, we've been focusing on heights of adult men, but there are all sorts of other variables we could have been looking at that are also normally distributed. We could have been talking about heights of women, or heights of 14-year-old girls, or heights of horses, or heights of dandelions. Or instead of talking about men's heights, we could have been talking about their IQ, or their blood pressure, or how far they can throw a football. Those are all continuous variables, and they all might be normally distributed. I don't know for sure whether they are, but they certainly could be. And they wouldn't have the same scale. It wouldn't be the same number right in the middle for the average. You'd have different numbers, but it would still have the same basic shape of this bell-shaped curve if we are in fact dealing with a variable that is normally distributed. So normally distributed means that the distribution follows the normal curve like this, which is symmetric. So if you drew a line right through the middle, it would cut it into two halves that are the same size and shape. They're just mirror images of one another. And the mean and the median and the mode for a normal distribution are all equal to one another. They're all at the same place right there in the center. So the most common value is also the average, is also the value where there's the same number of values above it as there are below it. And about 68% of all the values are within one standard deviation of the mean, and about 95% are within two standard deviations of the mean. And because we have all these different scales for all these different variables and things that we could measure, we'd like to have some way of seeing what they have in common and standardizing all those different scales. And the way we do that is we can take all our data values and convert them to z-scores, like we talked about earlier in the semester in chapter 3, by calculating z equals x minus mu over sigma. So for a man's height, we could take that height minus the average of 69 and then divide by the standard deviation of 3 and get what the z-score for that height is. So if a man is 69 inches tall, the z-score, 69 minus 69 divided by 3, is 0. For a man who's 66 inches tall, the z-score would be 66 minus 69 divided by 3, which is -1. And that tells us that 66 inches is 1 standard deviation below the mean. 72 inches is 1 standard deviation above the mean. The z-score there is 1. For 63 inches, the z-score is -2. For 75 inches, it's +2. And so we can convert the original values to z-scores and get what we call the standard normal distribution, with 0 now in the middle, and then positive numbers 1, 2, 3, and so on going off to the right, and negative z's going off to the left. So if we take our original data values, convert them all to z-scores, we get a bunch of z-scores, and if our data was normally distributed, then our z-scores are going to have an average or mean of 0, right in the middle, and a standard deviation of 1. And that makes things easy to work with. And so the standard normal curve looks like this. It's got 0 in the middle. The z-scores are along this horizontal axis here. So z falls somewhere along this scale. Right in the middle is where z is 0. And then going off to the right, the z's get bigger and bigger. Going off to the left, they get smaller and smaller. You got the negative z's on the left and the positive z's on the right. The total area under the curve is 1. And then the area of the left half, to the left of center where the z's are negative, is 0.5. And then the area of the right half is 0.5. So half the area is over here on the left, and the other half is on the right. So 50% of z-scores for data values are below, so 50% of the z-scores are below 0, and the other 50% are above 0. About 68% of z-scores are between -1 and +1. About 95% of z-scores are between -2 and +2. And so that does it for the introduction of the sort of the big picture, the what and the why. And now it's time to start getting into the how we actually convert between z-scores and areas or probabilities or proportions or percentages. And there's different ways you can do this. There's different methods you can use. You can use a table, you can use a graphing calculator, you can use an app or a web-based application. So I'm going to make separate videos for some of the different methods. You don't have to know all the methods, you just have to know at least one that you really know how to use and that works for you. So I'm going to come back in separate videos and talk about how those methods work and how you actually do the translating between the z's and the areas and all that good stuff.